here d by dt of rho and area I'm taking outside, that is dh by dt of control volume, that is equal to mass flow rate minus kh. Initially height, whatever the height which are varying with respect to time, that will vary something like a very fastly, it will vary. Why? Because let's say you have mass flow rate, it's fixed, let's say you have 50 kilogram per second initially you have supplied, and initially height was zero at the time t equal to zero, so there was no liquid which are going out. The liquid which are going out was zero from here. After time t equal to 1 second, again 50 kilogram per second has been supplied, but now height will be increased during 1 second. So what will be happening? The mass flow rate which are going out will be some value, let's say that value is 5. How much of difference now? 45. And that difference is very large, and that will suits this dh by dt slope, or the h value as compared to t, it will rise at a very very faster rate. Now after t equal to 2 second, what will happen? It will be fixed 5 kilogram per second. Again it will rise to 10. The difference is 40. Again time t equal to 3 second, we gonna have 50 minus 20, 50 minus 30, 50 minus 40, 50 minus 50. So what is happening? Initially the liquid is rising, height of the liquid will rise at a very very faster rate. Now that faster rate will become what? Slower rate, because the difference is what? Getting decreased. See that 30, 20, 10, it will become zero. When it will become zero, the slope dh by dt after some point of time has to be zero. And my dear friend, which graph is showing you dh by dt equal to 0 after certain point of time? After certain point of time, there has to be steady state condition that to be reached, and this slope is 0. Either A is correct or D should be correct, but we will see which is correct. B cannot be correct because again they are saying that initially the slow initially it is moving, initially height of the liquid is getting generated in the container at a very very slow rate, and then it is become faster rate. Very very blunder. C option, it is a very very foolish kind of thing. That means who doesn't know anything about the fluid mechanics, they will take option called C, because it is saying that height will be continuously rising. How? Why the height will be rise continuously? Even I am showing you that the driving force will be zero, that dh by dt has to be zero. Definitely A or C, A or D should be correct. B and C is eliminated. Now the question mark, whether, see what you are understanding, it is increasing at a very very rapid rate. See that slope is higher, and after that this rapid rate is decreasing. That is a perfect graph, so A should be correct. But here in the case of D, it's shooting like anything, and then it will become constant, and that too it is varying linearly. Again I will show quantitatively that the graph is increasing, height will be increasing, height will increase exponentially. And what is the quality of exponential graph? It has to be asymptotic after a certain point of time. If it is decreasing, it should be like this. If it is increasing, it should be like this. But D graph is showing linear variation. Definitely wrong. Definitely wrong. So I hope that this particular thing is quite clear. Because these are the thoughts that will be coming in examination hall. These are the thought processes that will be coming in examination hall, because initially it has to be higher. Why it is coming at a very very faster rate in your mind? Because you can see by this relation, who are not aware of this, definitely they are gonna they have to leave this question simply, because mass flow rate which are going inlet and which are supplying, that is constant, and this is varying, and that is proportional to height h. So as we keep on supplying, generally the discharge will happen. Discharge will happen, height will decrease, increase, then it will decrease, and after a certain point of time, it will be become constant, steady state, right? This whatever we have seen, that is a qualitatively we have seen, qualitatively we have analyzed. Now let's see the quantitative wise, what we have to get from this question. Quantitatively, again you might be thinking, sir, from exactly again when you solve the Singer and Simbala unsolved example or solved example, good problems, there you will find this type of questions, right? Now here dm by dt, of a control volume will be mass flow rate at the inlet section minus mass flow rate at the outlet section. D by dt of rho A H, that is equal to mass flow rate. I'm calling this to be mass flow rate m dot minus of K, that is constant, into small h, because they have clearly, very clearly, they have given the mass flow rate is proportional to the height of the liquid. Initially the liquid, initially there is no liquid in the drum, so there is no height, there is no discharge. But as the height will be increasing, your mass flow rate which are going out will also be start increasing. Understand? Rho A into dH by dt, mass flow rate minus of K into H. Again, we can write dH by dt, that is equal to mass flow rate by rho A minus K divided by rho A into H. Now here we can write dH by dt plus K by rho A into H, that is mass flow rate divided by rho A. This equation, when you compare something like dy by dx, in mathematics you might have studied Py equal to Q, where P is what? K divided by rho A, and Q is what? Mass flow rate divided by rho A. Where integrating factor, what is the integrating factor? E to the power, here you have P into dx. P into dx is what? Dt here. So here e to the power K divided by rho A into T. Now when you put that, and after putting that, when you solve it, you will getting H. I am not solving the further equation, right? Y into integrating factor, that is Q into integrating factor into dt. You will get Hs minus mass flow rate divided by K e to the power minus of K divided by rho A into T plus mass flow rate divided by K. This is the equation you will get. And this equation is what? Exponential equation. Exponential. Any value of time t, when you put, this quantity will be always be lesser than this quantity, then obviously h will be always gonna increase as you proceed with the time. It will be always be giving you the higher and higher value, so make a note of it. Now, so this is what about the session of 2017. But here we have one more thing. Again we will solve 2017, that is set 2. Set 1 we have seen, now we will start set 2. In this session only we are discussing both 2017 set 1 and set 2. In 2017, that year they have conducted 2 times, right? So here we will do, okay. So very first question we will see set 2 2017. In our next session I will be discussing 2018, and then after that session we will be doing 2022 or 2020, because the last time paper conducted was 2020 only. Now again read the problem. The water tank is located, 3 meter above the ground. The depth of water in the tank is 2 meter. The exit of the pipe is 50 mm in diameter and 50-meter long. The velocity of the water at the exit at the ground will be what? So simply if I make the diagram, for the sake of simplicity here, if I make the diagram, here we can make to the next. This is a tank which is being located, and here we have the pipe. which are being there on the ground. Now the tank liquid is what? How much of uh, liquid in the tank? 2 meter. And what is the what they have given? What is the height of that particular tank from the ground? The water tank is located 3 meter above the ground. 3 meter above the ground. That means from here to here, it's a 3 meter. They are asking what is the discharge at this particular point. The friction factor in the pipe, the diameter, everything they have given. Diameter is 50 mm. Friction factor 0.02, 0.05, sorry. Friction factor 0.05, 0.05. So here friction factor will be 0.05, and G value they have given 10 meter per second square. And they are asking what is the length of the pipe. Length of the pipe they have given 50 meter. The total length of the pipe from here to here. This length they have given as 50 meter overall. Consider point 1 here, point 2 here. Apply Bernoulli equation between point 1 and 2. P1 by rho g plus V1 square by 2g plus height we are calling Z1. The point 1 height from the datum. Let me consider here datum. That means Z2 will be 0 and Z1 will be 5 meter. That is P2 by rho g plus V2 square by 2g plus Z2 plus head loss due to friction in a pipe. That is a major loss. Minor loss we are not considering over here. Now, at the particular surface, P1 will be 0, atmospheric pressure. P2 will also be 0 because of atmospheric pressure. They will cancel out. V1 is what? 0 because of the large tank. And Z1 is what? 5 meter. So put that value. Head loss due to friction will be FL square divided by 2GD. So 5 equal to V2 square divided by 2G plus F is what? 0.05, 50 into V square. V square that need to be calculated 2 into 10 into G into D. D is what? 0.05. So now from here when you take 0.05 into 50 divided by 20 divided by 0.5. So you will be getting 2.5 V square plus this will be 0.05 V square. As compared to 2.5, this 0.05 is almost like a negligible. So we can neglect. So now V square can be written as V square can be written as 2, where V can be written as root 2, that is 1.414 meter per second. 1.414 is approximate to what? 1.5. A will be correct. Even though you want to consider 0.05, unnecessarily you will add or make your calculation complicated. Because of under root and all, that's a difficult. Again, you will get 1.4 only, under root of kind of root 2 nearer to that value only. But yes. So that is what we got. The velocity at the exit at the ground will be approximate to 1.5 meter per second. That is the answer for 23rd. That is the answer for 23rd. Moving on to the next question. Note down. Isothermal compressibility will be how much they are asking. Isothermal compressibility. First of all, compressibility. What is the meaning of compressibility? That you must know. Then the second thought will come about the about what we call isothermal compressibility. Right, so here, note down. What is the meaning of compressibility? What is the meaning of compressibility? Compressibility basically reciprocal of the bulk modulus. That means compressibility we define by, let's say, K, but that will be inversely proportional to bulk modulus. What is the bulk modulus? Bulk modulus, everyone know that dP divided by minus dV divided by V. That thing we know. That's a pretty thing we know. So K will be written as, here we can write minus V dP divided by dV. So here this will be V dV divided by minus V dP. Now they are asking isothermal. So for isothermal we have to write temperature to be constant. So we can write 1 upon V dV divided by dP, temperature that is constant. That's it. No rocket science here. Whatever the formula you know, compressibility, simply multiply with that you need to take at constant temperature, right? So here we can write, for ideal gas we know that PV is equal to nRT. Then here V can be written as nRT divided by P. V can be written as nRT divided by P. Put that value into that KT, minus 1 upon V d by dP of nRT by P. So what I will be getting, 1 upon P nR T constant, d of dP of 1 upon P. So what you will get, minus nRTV, 1 upon P will become what, minus 1 upon P square. So what you will be getting, nRT divided by Vp square. Which option is correct? B is correct. That is the KT. That is the KT. We are not only having isothermal, we do have, my different isentropic compressibility also. That also you please note down. Isentropic. This particular question is belonging to thermodynamics, not exactly to the fluid mechanics. Isentropic compressibility we can write minus 1 upon V. Formula will be same, but the only thing is that entropy will be constant. Entropy will be constant here. Whereas means for a particular entropy, you have to, whenever we are writing suffix like s, that means s will be constant. Whenever we are writing t, that means t will be constant. That is called isentropic compressibility. No doubt. For ideal gas, kT will be 1 upon P, alpha will be 1 upon gamma times of P. Because for this, how you will find? You will find PV to the power gamma equal to constant. From here, you will be calculating further. Gamma is a specific heat ratio. How we are getting kT equal to 1 upon P? That's a very simple. That's a very simple, guys. Don't ask me why. See here, kT we have written minus 1 upon B. See how we are getting kT. See from that same expression, my different kT we know minus 1 upon V dV by dP at constant temperature. PV equal to nRT P into dV plus V into dP, that is equal to 0 for a constant temperature process. So from here dV by dP will be minus V divided by P. So here minus 1 upon V minus V divided by P, and that's how you will be getting 1 upon P. But P we know that multiply and divide by P, you will be getting P by P square, because P you know nRT by Vp square. So by this also you get the answer called B. All I want to say, you are getting answer 1 upon P. Either this is correct and this is also correct in both the way, right? This is the solution for this 28th problem. Moving on to this question again. In the last class, I clearly given which are all the invert flow reaction turbine, which are all the axial flow turbine, which are all the impulse turbine, or we also call tangential flow turbine. We also call tangential flow turbine. And one and only we have Pelton turbine. C will be correct. Question number 33. Now moving on to the next particular question. Now here in this question, you might be having little trouble, because whatever the value you know, that may not be given in the particular discussion. Why? Not down. Specific heat when you do here, it's not on the range of specific speed for a Pelton turbine, not on the range zero point zero 0.03 to 0.03. Then we have Francis turbine. We also call this to be high head and low discharge turbine. High head and low discharge turbine. Please remember that. Francis turbine we have the value zero point 0.3 to zero point 0.2. And then for the Kaplan turbine, we have the value point. Sorry, it's not a zero point 0.3. Oh, that's my mistake. 0.3 to 2.0, then 2.0 to 5.0. So you have the range which is given in the option A. That is correct. Generally, when we follow any textbook, in textbook, what the speed, specific speed range they have given. They might have given 0 to 60 like this, then 60 to 300, then 300 to 1000. This type of range they might have given for this Pelton, Francis, and Kaplan. But remember that they have calculated a specific speed when they kept the power in terms of horsepower. Horsepower. When you convert into watt, then you will get this particular range. See, what is the power? What is the specific speed? Specific speed n into root p divided by h to the power 5 by 4. This is the formula we have. Here we generally keep n value or p value in kilowatt. In kilowatt, right? But whatever the range they have given, that seems to be the range they kept when they're keeping the value of power in terms of watt, not in the horsepower. This is the range for horsepower. Understanding my point? So there you need to be a little bit careful. Now, all of you might have understood what I was talking about. Here, try to see this question and try to solve. Apply the mathematic equation at a lowest level. Lowest level will be I'm considering here at point P at point Q. Pressure at point P has to be equated to pressure at point Q. Okay, so to solve this particular problem, I will be taking PP equal to PQ. Here only I'm writing here. What is the pressure at point A? Pressure at point A will be PA plus, because of this liquid 1, and I'm calling this to be liquid 2, rho 1 G into H1, that is equal to pressure because of this particular column height, that is rho 2 G into H2. Do not add do not add anything about the atmospheric pressure because they are asking gauge pressure. Gauge pressure means no need to add further any atmospheric pressure, that is considered as zero. Now, what will be the gauge pressure then? Rho 2 G into H2 minus rho 1 G into H1. So PA gauge pressure will be rho 2. What is the rho 2? What is the rho 2? 12,000 into G. G is what, 10 into height. Height is what, 1 minus 1000 into 10 into height 1. Height 1 is zero point 0.5. So when you put the value in kilopascal, how much of value you will be getting? 12,000 into 100, 12,000 into 10 minus, you will be getting here rho, that is 1000 into 10 into zero point 0.5. So you will be getting 115. 000 Pascal, you will be getting gauge pressure as 115 kilopascal. B will be correct. B will be correct. No doubt. Moving on to the next question. Question number 61. It is little bit conceptual regarding the metacentric height. Not as quite straightforward, because metacentric height we know theoretical formula, but they are asking experimentally what will be the formula to calculate this particular metacentric height. For that, I need to explain you little bit some derivation. Now, directly formula we have geometric GM calculation, W1 into X divided by W tan theta. This is the formula used to calculate metacentric height GM experimentally. Experimentally, we know this particular data, and theoretically, I by volume displaced minus of BZ. This is the formula we know theoretically, but there's no such a data is being provided to calculate GM in terms of theoretical manner, like I by volume displaced minus of BC. They have not given anything regarding moment of inertia. I minimum, rather to say here I minimum. But now here you can put the value of GM W1. What is the W1? Mass of the here mass of the here W1 is nothing but mass of the cartoon. Mass of the cartoon. Here W is nothing but mass of the vessel or weight of the vessel. Rather to say mass, here I will be saying weight of the vessel. Weight of the vessel. Weight of the vessel, including vessel weight plus cartoon weight, both. So now when you put W1 you will be getting 50. It has been displaced by the amount 2 meter divided by W will be given as 10 ton. 1 ton will be 1000 kg. Tan theta will be 0.01 into 180 by pi. So now when you do that, you will be getting 1 meter as an answer. But how to proceed, how to do the derivation of this particular formula that we are getting, right? So that is a very important. Now how to proceed here? Let's check it out. Experimental method to calculate the metacentric height. We have certain, let's say the ship which is being floating. And symmetrically we are placing the cartoon like this. We are placing the cartoon like this. Whereas W1 and W I have shown the weight. Now here we have G, here we have B. Center of gravity, center of buoyancy, center of buoyancy. When I tilt this, tilting means simply place the object. This small object you place here. When you place here, definitely it will be start tilting in this manner. And sorry, liquid surface cannot be tilted. We cannot tilt river actually. Yeah, that will be same only, but the surface of what we have drawn with the red color, that ship, the ship will be tilted like this. Now the weight is here. It has been displaced by the amount x. Definitely, when the mass is shifted, the total weight will also be shifted. And let's say the shifting has been done initially G, B. Now they will be getting shifted to Z1 to B1. Or rather to say here, we will draw nearer to that. Here we can draw here somewhat Z1, B1. Now when I draw the vertical line from this, I will be getting metacentric height G. So what your understanding is this particular line I'm making? Here we can make perpendicular. This is theta, and this particular height will be Gm, which tells you the value of Gm will tell you whether it is a stable or unstable. From a triangle, okay, I'm not giving any name for this triangle because again that will be confusing. Now, initially when you consider the weight W1, because of this it will be start disturbing like this. like this, further and further. But what about this weight, the total weight? It will be start doing applying some restoring torque, and it will be start shifting this to original conditions. So the see, just like a pen, this is a pen. Again it will be disturbed, again stable, again disturbed, again stable. So definitely the moment about m point has to be zero. The net moment about m point has to be zero, right? That means in the static equilibrium condition, moment due to small box, moment due to small box or cartoon, we can write w1 into x like this. You can see force into perpendicular distance, right? And moment due to uh, complete vessel weight plus cartoon weight, that will be w into what about this distance gg1, this will be gg1. But what about gg1? This is nothing but gg1. I'm writing here once again. See, this is a perpendicular, this is theta, this is gg1, this is the end point, this is the gm. What about tan theta? Gg1 divided by gm. So what we can write? W into tan theta. At this static equilibrium condition, both these moments should cancel each other. So what we can write? W into x, that is equal to W into tan theta. So here into Zm. So into Zm. So Zm can be written as W1 into x divided by W tan theta. Make a note of it. Make a note of it. This is an experimental thing, because you know that the metacenter point by definition is a point about which the body will be start is making a small oscillation, just like a pendulum. When you disturb the pendulum, it will be going like this, coming like this, coming, going like this, coming like this. So every data is given to you to solve this problem. Remember this, they have given radian. You have to convert in degree by applying 180 by pi. Okay, once we got this thing, we can move on to the. That's all about the question. In the last particular class, I told you that we will do one derivation of Pelton turbine. I have uh, told you that how we are getting U equal to V1 by 2. That particular derivation we will do, and then we will close the session. Here we will do that derivation, Pelton turbine. Hydraulic efficiency of a Pelton turbine. Hold on. Pelton turbine operating with maximum efficiency. So you know that hydraulic efficiency will be, everyone know that that is hydraulic efficiency. We know that what is the hydraulic efficiency? Hydraulic efficiency, when you write run power by water power, run power by water power. What is the run power? Run power, you know that rho q into v omega 1 plus v omega 2 into u divided by water power will be rho g qh. But here, when you see the diagram, when you see the diagram of a Pelton turbine, you will have something like this, where the water is being impinging with the velocity v1, and that will become p omega 1, where this triangle will become like this. This will be vr2. Again, if I make here, this is phi, this is what we call beta, and this is we call vf2, and this we are calling with the red color which I am marking here, v2. From here to here we have u2, and from here to here we have v omega 2. So now clearly, if I write in terms of everything, hydraulic efficiency can be written as v omega 1 can be written as v1. What about v omega 2 from this diagram? Can we write vr2 cos phi minus of u2? Yes, we can write clearly. So here we can write 2 times of here rho g qh, that is equal to half of mv square, half of mass flow rate into v square, that we can write. So there we are replacing with the 2 uh, rho q. Here if I write half of mv square, then this mass flow rate, what is the mass flow rate? Mass flow rate, we know that rho times of q. So hydraulic efficiency can be written as rho q v1 plus vr2 cos phi minus u into u. u2, that is equal to u1, that is equal to u because of tangential flow. Half of rho q into v1 square. So this will cancel out. So we can write 2 times of v1 plus. Now what is the vr2? vr2 we can be written as vr2 can be written as k times of vr1, k times of v1 minus u1, where k is nothing but friction coefficient, into cos phi minus u into u divided by v1 square. Now you have converted everything in terms of what we call uh, phi is a blade angle at the outlet. Phi is a blade angle at outlet. So now you differentiate this hydraulic efficiency with respect to v1, sorry, with respect to u, and try to equate to 0. Try to equate to 0. What you will be getting here? You will be getting here something like multiply this v1 with the u. You will be getting what? v1 plus s cos phi v1 minus k times of 2u cos phi minus 2u. But again, that is equal to 0. So what we can get? v1 plus k cos 5 minus k into 2u cos 5 minus 2u equal to 0. So from here we can get v1 minus v1 we can get we can v1 we can take outside, and here we can write k cos 5. Sorry, here we can write not like this. K minus sorry, v1 minus 2u into cos phi into k, that is equal to 0. So overall I am taking v1 minus 2u outside, 1 plus k cos phi, that is equal to 0. So now here if I equate v1 minus 2u, that is equal to 0, u will be what? v1 divided by 2. That is the condition for having Pelton turbine maximum efficiency. Make a note of it. And remember, this is only valid when we have nozzle efficiency. Here we have taken nozzle efficiency, that is 100%. Please make a note of it. Here we have kept the nozzle efficiency as 100%. Right. So we have done regarding all the solutions, like all the particular question of 2017. Right. So thank you all.